Okay. So this is the last hour of Physics 1C for May 11th, I think. And we're going to be talking... We're now finally moving into a new chapter. This chapter is on inductance. Okay. Inductance is often referred to as self-induced EMF. Well, it's not exactly referred to as this, but it is something that we are going to measure when you have self-induced EMF. Okay, so let's start off with a circuit. Let's just keep things like really simple. We'll just draw a circuit that has a battery, a switch, a resistor, and then we're going to add something that we haven't really done in this class, which is we're going to take a circuit and we're going to intentionally add a coil of wire. So think about it, this is adding basically like a solenoid or something into the system. Like this. And you don't even need to do this, but I think it kind of clarifies what's going to be going on here. So system is battery with some EMF, positive side here, negative side here. We're going to throw the switch at t equal to 0. I'm not going to write all that out. I'm just going to say at t equal to 0, and I'll put that little arrow there to indicate that we're throwing the switch. When we do throw the switch right here, what's going to happen is that current is going to start flowing in this direction. Okay. Now, that current is not going to build up instantly. It's going to take time for that current to actually reach a maximum value. So let's say that at a moment in time, I represents the current flowing through this circuit. That current will also be flowing around all of these coils over here, right? But we know that in this case, the current flowing through the circuit is increasing, right? Right? Current is increasing. And as a result of the current increasing, that means there's going to be a magnetic flux through these coils of wire right here, right? In fact, we know what direction the magnetic field produced by this current is. It's going to point kind of down this way, right? If the coils are curling around this way, there's going to be a magnetic field inside of that. We'll just call it the magnetic field of the solenoid or something like that. And that's due to the current that's flowing right here, yeah? But the increase in current means that there is an increase in magnetic flux through those coils, right? So phi b, magnetic flux through the coils. Yeah? And what happens after that? So current's increasing, which leads to an increase in magnetic flux through the coils. Now this is an increase in flux due to its own magnetism, by the way. This is why this is referred to as self-induced EMF. It has magnetism, but it also, that same magnet, that its magnetic field that's building up inside of this, is representing a changing magnetic flux through the coils. So what happens as a result of that, as a result of the increase in flux through the coils?
Is there going to be an induced magnetic field?
Yeah, there's going to be an induced magnetic field. In what direction does it need to point?
Opposite.
Opposite, yeah. So there's actually going to be an induced magnetic field that goes opposite. I don't know how well I can draw another. So this is going to be our induced magnetic field, which is going to point back the other direction. And that's going to have the effect of, well, when we say there's an induced magnetic field, really what we mean is there's a self-induced, there's an EMF that's induced, right? And that EMF basically has to be induced back in the opposite direction. So there's also going to be an induced EMF back in the opposite direction. I'm going to call it IND. Okay. It's sometimes referred to as back EMF or back current, reverse current. I don't know. There's all kinds of names for it, but it's a kind of back EMF that gets induced in the system because you have a coil in the system. Okay? So increased flux in the current over time leads to what we call back EMF, which is an induced EMF opposite to the change. Okay? So it's called back EMF. That's the name I'm going to give to it, is back EMF. It's induced EMF opposite to the change in flux, or the change in current, or whatever. So what this means is that when you have a system like this, the current cannot develop instantly, okay? So the current cannot instantly release its max value, which in this circuit, what would the current max value be?
E over R.
E over R, exactly. The EMF divided by the resistance of the circuit. So it's going to take time, basically, for the circuit to actually reach a maximum value. And how long it takes, well, it's going to be related, as it turns out, to, I think it's R over L or something like that. But I haven't said what L is yet, sorry. The point is, it's going to take time. Okay, so we call this self-induced EMF because, everything we've done before this, you had like two circuits. You had like one circuit that was a solenoid, and you wrap a coil around it and find out what the EMF induced there was. Or you have a coil, and you place a magnet into the coil, and by pushing the magnet into the coil, the external magnetic field induces a current into another wire, right? Well, that same effect, you can't stop it from happening, right? It's a physical effect that occurs with the way that magnetic fields work, that if you try to change the current flowing through a circuit, even if all you're doing is just turning the circuit on, you are automatically inducing an EMF in that circuit that goes the other direction that will prevent the circuit from instantly reaching the maximum value. It'll take time, basically. Okay? So yeah, we call it self-induced EMF. It's also referred to as back EMF because it's going to tend to be opposite the direction of the change in current. This same thing will occur when you try to turn the circuit off. Okay, when you try to turn the circuit off, there's a decrease in flux. When there's a decrease in flux, there's going to be an induced EMF that goes in the same direction as the current was already going, and will keep the circuit going. We'll talk more about this stuff later, but do you all understand the effect and what's going on here? Does this make sense?
Yes.
Yep.
All right, let's look at the book's picture. The book has a little bit better picture of this. So here's the book's picture. So here they have a circuit. You've got a current carrying wire right here, and then you've got this right here. So it says, the current I in the circuit causes a magnetic field B in the coil, and hence a flux through the coil. Self-inductance, if the current I in the coil is changing, the changing flux through the coil induces an EMF in the coil. Right? Okay. So we can give kind of a name to this effect, and we can actually give a name to this little piece that we added to the circuit here. The coil, we're going to call it an inductor because its job is going to be to intentionally induce EMFs in itself, and the goal will be to smooth out current fluctuations. Because the current cannot instantly reach its max value, there's a time that it takes to reach maximum. That means having coils in your circuit leads to smoothing out current fluctuations. It smooths out changes in currents. It makes the circuit so that as you try to flip the current to go one way and then back to the other way, the circuit itself is going to have an effect that either slows down your attempt to increase the current or slows down your attempts to turn off the current by making the current continue to go in the same direction, basically. Now, when we intentionally put one of these coils into the circuit, the coil itself is referred to as an inductor. An inductor. The symbol we're going to use for an inductor is basically this. Okay, that's like the current symbol or the circuit symbol. It's just going to look like a little coil right here. At the end of the day, when you see the word inductor, if you're confused by that, you should think coil of wire. Okay, because I think the word inductor is a little bit confusing. Coil, you understand. Loop of wire, you understand, right? This is just wires that are wrapped around, right? Inductor, they mean the same thing. Okay. All right. So we use the symbol like this, and the symbol we use for inductance is L. Okay, and I don't know how to derive this, so I'm just going to tell you what it's equal to. So the value of the inductance is going to depend, probably not too surprisingly, on the number of coils. The more coils that you get, the bigger that this effect of smoothing of currents is going to be, and we multiply that by magnetic flux. Contained within the definition of magnetic flux are things like the size of the magnetic field and the area, and then we divide this by I. Okay? And this expression we call inductance. We call that inductance. We can do a really simple calculation to show you what this is equal to by using a solenoid, because we know all the information we need to know for a solenoid. So I've told you what the word is. I'm going to do a calculation, and then we're going to look at how these inductors behave in circuits, assuming that the FET version of that works. So let's find the inductance of a solenoid. And again, inductance represents how good an object is at inducing currents. That's what it means. How good is it at having currents induced inside of it? So inductance of a solenoid. We love doing things with solenoids because they are very, very straightforward and simple. So we'll take a solenoid. I don't want to spend too much time drawing a picture, but I need to make it like somewhat not crappy. So this will be one end of our solenoid. This will be the other end. We'll connect it with a little tube here. Try to make things straight, because it's okay if it goes down at an angle a little bit. Shapes. Okay, so there is our air core solenoid. We want to erase part of this so that we can have one end be facing us. So we'll erase this piece here, and then just kind of close it like that. That. Okay, so it has an end cap with an area A. The solenoid is made of wires. Let's say that the wires come down like this and then wrap up this way, and they eventually come back up here and wrap around this way. And we just continue that. I'm not going to draw too many of these. Get the idea. There are loops of wire that are just wrapping around until eventually they come out like this. We're going to say the current flowing on our solenoid is capital I. The current's going to flow out this side. That means it's flowing like this, like this, like this. I don't think we really need the direction of the magnetic field, but can you all tell me what direction it is? What direction does the magnetic field point here? It's either going to point to the right or left. What is it, right or left?
Left.
Right.
It's right. Again, you just basically like curl your fingers the direction the current's going. Your thumb points to the right. Almost like as if you're gripping it with your fingers kind of just following the direction of the current.
Yeah.
Your thumb goes right. So this is going to have a magnetic field, and we know that it's basically going to kind of point like this. Whoops. It's going to kind of point like this. We're going to kind of make the same assumption we normally make with solenoids, which is that the magnetic field is roughly uniform, that it's equal to mu naught times the number of turns per unit length multiplied by the current. And let's, just because of the way this is written up here, let's write this as the other version of it, which is mu naught n divided by L. So I can also include on here that L is the length of the solenoid. As long as there's turns, that's include the length times I. All right, so what's the inductance? Well, the inductance is equal to the number of turns times the magnetic flux. Magnetic flux is just going to be a magnetic field times the area, so NBA divided by I. And then we do basically N. Magnetic field is this. What almost all, I think it has to happen when you're doing these kind of calculations. The current always cancels out because you want your inductance to have nothing to do with the specific currents that you send through the circuit. You want it to just be kind of a value that is independent of the current that you pass through the circuit. So we end up getting, it looks like I left off something, right? I left off an A. Area. So it looks like what we have left is mu naught, the number of turns squared, divided by the length, and then multiplied by the area. This is the inductance of a solenoid. Okay, again, capital L is what we use, that's the symbol for inductance, and this is the inductance of a solenoid. You'll notice, well, let's just look at the equation. You'll tell me. What do you notice about this equation? What does the inductance of a solenoid depend on?
The area, the length, and the number of turns.
Yeah, and then this is obviously just a constant. Now, you can increase mu. So this value of mu naught, this is the value if the center of the solenoid has air in it, or empty space, basically. If you put a magnet in there, or sorry, if you put like an iron core in there, I think the value of mu can increase by a factor of like 100 to 1,000 or so. So you can get even bigger inductance by putting like iron inside of this, for example, or different other materials. But that's kind of more specifics. But the point is that, yeah, so you can get more inductance by putting iron inside of it. The main thing that seems to show up here, though, is the number of turns, right? They're squared. And no matter what size you have, A and L for your solenoid, like I would assume, if you're trying to get something that has a really big inductance, you can obviously make A really big and you can make L really short, which would look like what? That would be like something like this, right? A bunch of rings just in one place. That would have a really short L compared to A. And then you just want to wrap as many turns as you possibly can, right? Because it's N squared. So if you can get 1,000 terms in here, it's going to be 1,000 squared. That's going to affect it. Okay, but notice what's not in here. There's nothing about magnetic fields, right? There's nothing about current. There's nothing about electric fields, charges, velocities, nothing like that. It's just the shape. It only depends on the shape, right? How fat is it? How long is it? And how many pieces of wire did you roll it together to get it, right? So inductance is purely dependent on shape, because the shape is going to control how strongly this object can have magnetic fields induced into it, can have currents induced into it, can have EMFs induced into it, right? Okay, does that make sense? Any questions about what an inductor is, what inductance is?
What are the dimensions of mu naught again? I kind of forgot. We could look
So
it up.
mu naught is equal to 4 pi times 10 to the minus 7, and the units are Tesla meter divided by amp.
Tesla meter, amps, okay.
Oh, actually, I didn't even say what the units of inductance are. So the unit for inductance is called the Henry. So 1 Henry, capital H. I think it's volt second per amp. I'm just going to write that down. We're going to write that down. We're going to see if that's right. So units of flux are volt seconds, right? There you go. I proved it. Because it's volt seconds over amps. The units of flux are volts seconds because of this equation. EMF is equal to ddt of flux, right? So since the dt can be moved to the other side, this has units of volts, dt has units of seconds, and then you have flux on this side, right? So flux has units. You can't see anything I'm writing. Oops. Sorry, move some of this stuff over. So from this equation, since dt has units of seconds, if we multiply the seconds over here, we'll have volts from EMF times seconds. That gives us this. So the unit of Henry has volt seconds per amp. What's a volt over an amp equal to?
Is that ohm?
That's an ohm, yeah. So the other unit that you can compare this to is ohm times seconds. Ohms times seconds. So the unit of inductance is a Henry. And so Henry actually is... Okay, I might be getting this wrong. I think he's an American physicist. I think he is. And I don't think his first name is Henry. I think his last name is Henry. There's something called Henry's law, which is basically Faraday's law. So I think, I may be misremembering this because I haven't studied this in a couple years. I think that Henry came up with Faraday's law around the same time Faraday did. But you've never heard of this guy, right? You probably had never heard of Faraday before you took this class, though, right? Right?
I've heard of Faraday.
You have heard of Faraday. What about the rest of you? Not you. Okay. Yeah. I don't think he's one of those scientists that we grow up knowing about. Like, you grew up, you learned about Newton, you learned about Einstein. You may know nothing about them, but you learned that Newton had an apple drop on his head, and you learned that Einstein's really smart. And you probably hear about E equals mc squared or something like that. I mean, you're more likely to have heard of Darwin, for example, than Faraday, right? Darwin is someone you certainly heard of, right?
Wait, really? You serious?
Why not? I mean,
Sure.
Evolution
is that true? Wait, what are the people saying?
We should do a poll. We should do a poll.
And in biology in high school, you learn about Darwin.
Well, also, it's just a really controversial subject, right? So at some point in time, you probably talked about evolution in... I mean, we talked about evolution in one of my English classes, right? Because we read that book about the monkey trail, or Scopes trail, or whatever it's called. About some teacher that was trying to teach evolution in Tennessee. Now, everybody has different, experiences or whatever. I'm just trying to compare, right? And I think Darwin is probably more well known than Faraday. So anyway, but if you take electricity, obviously you end up hearing about Faraday, or if you read anything about it, you'll read about Faraday. Doesn't mean you know much about him. I mean, we don't know much about a lot of these scientists, right? Because we mostly just study their theories, we study their ideas, we name units after them, but we don't learn much about the people themselves, right? Like, I don't know anything about James Watt, who was the person that we named the power unit after, other than he was involved in commercial selling of steam engines, I think. I don't even know if that's accurate. Okay, so we have this thing called inductance, and the next thing I'd like to do is, now that we kind of understand a little bit about what it is, I will say, by the way, that just like the other units we've learned in this class, 1 Henry is a very, very large inductor. I think the largest inductors we have at the school are 0.3 Henrys, and those are very, very, very big inductors. They are, they're actually about the size of this, and they just have coils just wrapped around them. It's like thousands and thousands of coils. It's just basically just coils wrapped and wrapped and wrapped and wrapped and wrapped. I mean, it's basically if you think about it, it's like a spool of wire. A spool of wire is an inductor. If you go buy a spool of copper wire, for example, it usually comes in spools. That would be an inductor, because it's literally just a bunch of coils of wire that are wrapped around a core. But yeah, 1 Henry is really big. The biggest ones we have at the school are about 0.3 Henrys. Most of the problems you're going to be doing, they're going to be talking about things that have millihenry inductances and stuff like that. But I think that now is a really good time to go to a circuit and look at what these things actually physically do in a circuit. Because what we're going to find is that they basically make circuits really sluggish to change, and that means that they act
in inertia.
In a very real way. They act like inertia, exactly. They act like inertia because they prevent you from trying to change the current. If the current's already flowing one way, the inductor makes it want to keep going that way if you try to slow it down. If the current's not moving, the inductor makes it hard for you to get the current going. Just like it's hard to get your car moving, but once it starts moving and it's rolling down the road, even if it's a flat road, it's quite difficult to get it to stop moving, right? It's hard to get it started moving, and then once it's moving, it's hard to slow it down. That's what inertia is, right? And that's what inductance is, basically. All right, let's see. I've used this semester, so I'm pretty sure this one still works. Now, the real question is, with some of these, sometimes they kind of break. Let's see. I've downloaded this 15 times now. It's kind of funny. Is it going to open? There it goes. Okay, so now what we want to do is we want to actually put an inductor in a circuit. Now we've learned now about, this is the third and last of the kind of things in a circuit we're going to learn about. We may talk about diodes at some point, but we never seem to ever get to that, and that's fine. But what are the pieces of a circuit we've learned about? Well, obviously batteries, wires, resistors, capacitors, light bulbs, switches, inductors. It's really the three things really that end up being in circuits, though, that we care about are capacitors, inductors, and resistors. Those are what are called the passive elements. They're elements that do things without having any moving pieces. Like batteries have chemicals in them, right? The resistor is literally just a wire that's, wrapped around a bunch of times in a very small kind of. It's just a long wire, pretty much. And the inductor is kind of the same thing. It's just that it's done so with a bigger area. All right, so what we're going to do is we're going to look at a circuit that just has an inductor in it. I think we'll put a light bulb in here too so we can actually see what's happening. So the light bulb is going to be kind of our visual representation of what the inductor is doing. Let's actually change the inductance. So this starts off at 50 henries. It's funny to me that the lowest value you can get here, 10 henries, would be. I suspect even if you worked in electrical fields, you'd probably never see an inductor that's this big. 10 henries is huge. I mean, it's just massive. Okay. We definitely don't have any 10 Henry inductors at the school, I'll say that much. All right, switch is open, right? Okay, let's put this down to 10 Henries. Let's, okay, what's the resistance of the light bulb? 10 ohms, okay. So the total resistance in the circuit would just be 20 ohms, right? Because these are in series with each other. And 10 Henries, okay, we'll see how this works. Okay, so also one other thing I want to do is, I guess we want an ammeter. And we'll just stick that right here. Actually, I want the one that plots. No, I don't want this one. I mean, I guess we could use it, but what I really want is a current chart. That's what I want. Okay. So obviously no current flowing through the circuit now because the switch is open here. But what we want to do is kind of observe what happens. The light bulb. So watch the light bulb. I'll put this right next to the light bulb. Watch what happens to the light bulb when I turn on this circuit. Okay, it did not come on instantly, that's for sure. The question is it going to come on at all? Are we paused? Oh, that was weird. Can I restart? Okay, there we go. It's like time wasn't flowing for some reason. I don't know why. Okay, so no current. That's 0, right? So let's watch what happens to this light bulb when I throw the switch. Ah, nothing. The light bulb is not connected. I just noticed. It needs to be connected to both sides of the light bulb. There we go. Okay. All right. It's like the 4th try. We'll try this again. Okay, time's going forward. There's no current. The switch is open. Now let's watch the light bulb. Okay, it gets bright, but it takes some time. And I guess we need to zoom in here. Let's go to like this. It looks like that's our maximum current, right? So let's go back and let's reset it. If I just click reset dynamics, we'll just automatically restart. Yeah, okay. So you can see it right there, right? That the way, I'm just going to click reset dynamics each time so you can see what's happening. The current starts off at 0, goes back to 0, and it just slowly reaches the maximum value. I guess this is the maximum value we're going to get out of this here, right? It does not instantaneously happen. Now, if we were to, let's see if I'm wrong about this. Let's open this. Let's reset dynamics. Let's get rid of the inductor so we can see what it looks like without the inductor, because I don't think it's super obvious. All right, let's try this again. I'm going to close this. Let's watch what happens to the light bulb. See how it's like instant? It just goes from there to there instantly. Again, I'll reset dynamics so you can see it again. In fact, now look, if I reset dynamics, you don't even see a change, just because of the way this system works. I would have to open the circuit to get to 0, then reset dynamics, and then close it, and it's literally instant in this system, because this is a perfect system. This system is also, so it would never truly be instant because, look, there's a coil of wire right here, right? And technically just having any loop of wire, it doesn't matter how big or small it is, any loop of wire has some self-inductance, basically, right? So this isn't really very realistic. It still should take a little bit of time to reach maximum, but it doesn't. Can we make it, let's make this brighter. Let's add some batteries in here. Let's see how bright that's gonna get. I'd like to be able to see kind of like a deviation. Okay, and then let's go back out until we can see there's the current. Okay, so again, just to remind you, it's like off, on, completely instant. You can see it in the graph right there, right? It's just instantaneous. It's like no energy, energy, no energy, energy. But there's something that's kind of ridiculous about that, and inductors allow us to manipulate and control this. So now if I connect this, we put the inductor in there. We do the exact same thing again. I'm just going to click this just in case. Close this. And yeah, it takes some time for it to actually lighten up, right? In fact, it's smoothed out over an even longer period of time here. All right. So what do you think happens if I increase the inductance? Right now, this inductor is 10 henries, right? So it's going to take longer, right? If we get a bigger inductor, that means that the back EMF is going to be bigger. Now notice you don't even see the back EMF on here. The way it shows up is that the actual current is just lower than it should be, in a way, right? So let's just change the inductance here. Let's have it go up to like half. We'll go up to like 50-ish. And now it should take a really long time for this light bulb to actually light up. Let's see if that's true. Click reset dynamics again. I'm going to click show value to indicate that we've gone up here. And I'm going to close this now. Much more gradual. And there it goes. Now it's fully lit. Now, what I'd like to do now is show you what happens when you try to turn it off. I have to figure out how to do that, though, because I need to create a path. So we need to add more to this so we can show what happens when you turn this off. We need a path that has an inductor that does not have a switch in it. So let's do that. Okay, so can you guys see how it's making the circuit kind of sluggish to respond? It's like it takes time. The way I think about it is that having that inductor in there basically, in a way, endows the entire circuit with more mass. It's like the electrons all of a sudden increased in mass. And then now it's just a lot harder to push the electrons left or right in the circuit. Doesn't matter which way you want to push them. It's just harder to push them around because it's like they've gotten more mass. Like they're heavier, like they're bigger boulders. It's almost like when you have a small inductor here, like if we change the inductance, and we go down to like 10, this is like a circuit that's like 1/5 the mass in a way. So that like here it's like the electrons are like pebbles, and then when we ramp this up and change the inductance to like let's say 100, it's like the pebbles have become boulders now that you're trying to push around. See it, this is really high. Oh, whoops. Okay, so let's show the opposite effect, because this has to work both directions for it to actually be like mass, because massive objects are not easy to speed up and they are not easy to slow down, right? If you see a large semi driving down the road at 60 miles an hour, you would never get in front of it and try to slow it down because you know there'd be no chance. Likewise, you'd probably never try to push a semi, but let's, okay, so we need to add another piece to the circuit now. And we're going to put an inductor in this piece too. This is where sometimes the circuit's going to catch on fire or something like that, but it doesn't really matter. Okay, so what I want to do now, we have the current flowing, right? What I want to do is I want to basically make it so that the current can only flow through the upper path. And I think that'll happen. How can we do this? We need to have a switch. I want to switch this one off and this one on, basically. All right, let's just do this and let's see what happens. So right now the current can only flow here, right? If I close this switch, I think it's going to make the current also flow through the top, right? That's probably okay. Yeah, it's fine, right? Because now I think what we can do is... Here, I want to do one other thing. Let's reset everything. No. Reset dynamics. Okay, so this is our circuit turning on. We'll wait until it gets to its maximum. So this is 50, and this is 100, okay? I think this will work. I don't know, we'll find out. So now what we're gonna do is we're gonna look at what happens when we turn it off. And let's get this down to where we can see kind of the full curve here. So now to turn this off, I'm gonna disconnect the batteries down here. And we'll do that by opening this switch. So I'll open this switch now. I was afraid of that. That's just gonna break. See? Oh my god. Well, okay, let's see if I can find a way to do this that doesn't involve putting multiple, because I think the more, when you put too much stuff into this program, this is almost always what happens. Because that's not what would happen in real life. Just throwing it out.
Everything just blows up.
Just throwing that out there. All right, we'll do this with a minimum number. So what we really need is, we need two paths, right? We need a path where the current flows. And we want the battery, the light bulb here. I don't know the best way to do this. Maybe you all could play with this and figure it out yourselves. Maybe I could give that as an assignment for you. To just show how all this ends up working. Okay, so if I connect this is automatically going to make it start moving. So we need to have a switch here. What I'd love to have is a switch that can switch between the segments of the circuit. I don't know if I can use these to do that, though. If that makes any sense. Like, I'd like to be able to have it go from one segment of the circuit to the other segment of the circuit. We do it with two switches.
Does it have to be instant?
It's not super important that it's instant, in which case we could do it with two, right? Is that what you mean?
Yeah.
Yeah, I think it's probably okay if it's not instant. Okay, so we want to put the light bulb... Okay, I think we want the battery here. What time is it, by the way? Oh, we should stop soon. Maybe I will give this to you as an assignment. Maybe you all can just try to do this yourselves. We'll see if this works or not. Okay. So this segment, if I turn it... Oh, there's no way to disconnect the top part now. We need to do it like this. Just remove it. We need a switch that just connects the top part when the middle part disconnects. That's what we want, right? Okay, I think this works. Pretty sure this works. I'm pretty sure the current is only going to flow through the bottom if I do this. Or will it?
Not paused.
No, but like, usually, like, once you get these kind of messages, this thing will just stop, like, you know, it'll just stop doing anything pretty much. as you can see. Yeah, I don't know. Maybe you all can play with this. I'll play with it too. See if you can construct a circuit out of this. I'm gonna put a link to this, so maybe you can all play with this. This is I don't know if this will run on your computers or not. I probably should, but see if you can make a circuit where you show what it looks like when you turn it off, basically. Does that make sense? Like, see if you can show that the light bulb basically takes time for it to like kind of decay, as opposed to like instantly changing. Does that make sense? Can you all try to do that for next time? Play with that and see what happens.
Does it take Flash?
That one doesn't. This one should run on pretty much anything because it's Java. Okay. Mostly I just want you all to play with the circuit. So even if you can't figure it out, just play with it. Try to break it like I did, you know. Do whatever you want. But see if any of you can come up with something, and I'll ask at the beginning of next class, see if anybody did. I'll play with it too and see if I can. But I would definitely be more interested to see if you all came up with something that, you know, maybe you'll find something interesting by playing around with this. But really what I want you to do, I'll write down to be more clear. See if you can construct a circuit so that I'll make this bigger so you can see it. So we'll try to do that. We'll call this some kind of lab assignment, since we're not able to do real labs. I want to make this bigger, so I have to go here and select. Where did my? Oh, there it is. Yeah. Okay. Can you all read that better?
Yep.
Yeah.
I'll put it in. This right here too. Oh, interesting. It's actually going to copy the. Whatever. That's fine. Yeah. See if you can do that, and otherwise, just kind of play with it. See if you can learn something from it.